Hey, welcome back to Fan Mama Physics. In this video, we're going to do some examples on the double slit experiment. This is Young's double slit experiment. The questions I will be doing are from the worksheet, or these questions here. So I want to do 3. I don't know how long it will take, so depending on how long the first example takes, I may decide to combine the examples into one video, starting with example 6. Before we start this example, there's a few typos I just want to fix. First of all, there's not a lot of pictures here, so there's some things that are missing. So we're gonna have to assume that's from the middle, and I think what happened was there was some combination of question with diagrams, so things might not match here. The other one is state the feature of this graph that shows that the slit width is negligibly small. Determine the wavelength of light. The red light is then replaced by blue light. Predict what would happen to anything separation by fringes on the screen. Okay, so we're going to start off this question first of all with A. Explain why light is able to reach the middle of the screen. So I'm just going to explain to you verbally, and then I'll jot down the key things. So when light hits 2 slits, assuming whether they're small or not, as the light passes through one slit, because it's very narrow, when the beam of light hits the slit, the little opening, it's going to start to diffract. And of course, the diffraction is going to be much less if you have, say, depending on the slits that you use. So according to Young's double slit experiment, what happens when light is incident on those 2 slits is that there's going to be some amounts of diffraction as the light passes through those slits, so that those particular points then become what we call point sources. So as light is incident on these double slits, they then form this diffraction pattern as it spans outwards. The light will be able to propagate and be able to reach the screen. Then why you will see some light at the M, which is the middle, is not only due to diffraction, but you also see it there due to interference that is occurring at that point as well, because the 2 diffraction patterns are going to there's going to be interference in the middle, so you're going to get both effects of diffraction at the sources as well as interference at point M. Okay, so here you're going to get diffraction at those slits, they become point sources, then the light from those 2 point sources will interfere at point M, creating a nice bright spot. Okay, and B, if one of the slits is covered, state and explain the intensity of the light at M. And we know that for interference, we add up the amplitudes due to the principle of superposition. So at M, we're going to get perfect interference, which then you get 2 times the amplitude. But because we lose one of them, we're going to half the amplitude compared to before. So whatever amplitude we had when the 2 sources were interfering, we're going to have half the amplitude. But don't remember, when we talk about intensity is directly proportional to the square of the amplitude. So in fact, we're going to get 1/4 of the intensity that we had before, because we lose out on one of the amplitude, and it scales by half, then gets squared, which then that becomes 1/4. C, state the feature of this graph that shows that the slit width is negligibly small. How to tell is if you take a look at the intensities, the intensity for the peaks is relatively the same. And because of that, by definition, we say that the slit width is negligibly small. The reason why for this one is not necessarily required of you, especially, if you are doing, say, higher level and you have to study the single slit diffraction pattern, then you will notice that for the double slit interference pattern is essentially, it matches the pattern of your single slit diffraction pattern. So for a single slit diffraction, the width of the slit will vary inversely with the band of the middle envelope. So if you have a very fat width, if your slit width for a single slit diffraction, then you're going to have a very narrow middle band. And because of that narrow band, then you're going to have varying intensities as you're going through the middle. Versus if you have a smaller width, that middle band is going to be more stretched out. So the intensity doesn't change too much in terms of the middle as you're going away from the middle. So that has to do, so question C, if you want to look more into it, has to do with the pattern of a single slit diffraction pattern, how that is related to your double slit diffraction pattern. So that's where C comes from. The reason, you don't necessarily need to know the reason for at least for the standard level. For higher level, you probably be able to use some of the stuff you learned in single slit diffraction pattern to figure this out. Not at this point, however. So we're also missing a couple information for question D, which I just drew a diagram here for us to use. So what is this diagram about? Here I am showing you the distance between the two slits for the double slit interference. Here the 100 meters is a distance from the slit to the screen where you would see the pattern. So given given this information, and what we also know is the separation of the two peaks. Here we know it is 0.5 meters. Then we use this equation that you've learned, hopefully, which is S is equal to lambda big D over small d. So what do all of these represent? S is the separation of two successive peaks, or two successive troughs, or the minimas. It's a distance between two, because the path difference is of a whole wavelength, which is represented by this number here, the wavelength. What we want to find in question D is the wavelength of light used, which should be roughly in the red light region. So to isolate this one, you could, but before that, let's just try to figure out what each number is. This is the separation between the successive peaks, which is the 0.5 meters. This big D is the distance to the screen, so that's the 100 meters, okay? And then this small d is the distance between the two slits. Not the slit width, it's a distance between the two slits, since we're talking about double slit interference. So that would be a 0.142 millimeter. Okay, so to solve for lambda, if we rearrange this, we get, we move everything to the other side, moving times d on both sides and dividing by the big D to isolate for lambda, which then lambda is equal to small d times s divided by big D, in which we substitute in all our numbers. Small d is 0.142 times 10 to the power negative 3, because it's in millimeters. Separation between the peaks is 0.5 meters. And last but not least, the distance to the screen is 100 meters. So if we put all of those in, 142 to the power negative 3 times 0.5 divided by 100, we get 7.1 times 10 to the power of negative 7 meters, which is roughly 710, or exactly 710 nanometers. That is roughly your red light. So that is D. Okay. Last question, E. The red light is replaced by blue light. Predict what will happen to the separation of bright fringes on the screen. So we're going to zoom in here, and we know that our fringe separation, is equal to the wavelength times big D times small d, and we are seeing what's going to happen to wavelength. What will happen to the separation of the bright fringes, or the S value, if wavelength increases. So if this, or actually no, wait, blue light, wavelength decreases, my bad. Okay, blue light decreases in wavelength, frequency increases though. Blue light, if wavelength decreases for blue light, that means our separation of our bright fringes S value will also decrease, meaning this the distances between these peaks are going to get narrower. So it's going to look like, okay, let me use blue to draw this. So it's going to look like this. It's going to be closely packed together, okay? So the bright fringes separation is going to get closer together. Okay, so that is question E. I am so sorry about all the numbers that didn't appear so well over here. I had to stop the video just to make up some numbers. Anyways, I thank you for watching. Hopefully this video was helpful. Good luck with your practices. Fan Mama Physics signing out.